Good morning and welcome to this webcast. I'm your host, Jennifer Wicks, coming to you from behind the scenes from Learning and Development. We're very happy to have you on board and joining us for this National Science Foundation Research and Undergraduate Institutions webcast brought to you by STEMnet here at the Office of the Chancellor. So thank you again for being here, for taking the time this morning. We'd like to know a little bit more about you, and with that, I'll switch back to our polls for just a moment while we get started here. We'd like to know, what are you most interested in learning about this morning in the poll just beneath me? And then also, which campus or organization are you joining from today? We'd like to know. Well, we will have Q&A after each presentation today, and look forward to your engagement in the chat pod throughout the entire session. And we'll have closing comments, of course, at the very end with maybe a little bit more Q&A depending on time. We will have captions available at the link that we've posted for you in the open chat pod as well. So just know that there are live captions available for you to access. And with that, I'm happy to present to you and introduce Dr. Frank A. Gomez, our Executive Director of STEMnet at the Office of the Chancellor. And with that, Dr. Gomez, I'll hand it over to you to get started.
Thank you, Jennifer, for the kind introduction, and a warm welcome to everyone out there. I hope you and all your families are healthy and safe. It's great you can join us today for another one of our webcasts, this time on CSU RUI Exemplars from NSF. This marks our 17th webcast to the CSU community. Higher education research indicates that student engagement is the most critical factor in retention programs for undergraduate students. A number of studies have shown that if students do not feel engaged, they are at high risk for dropping out. Among high-impact practices, undergraduate research has been demonstrated to have the most positive effects to promoting student engagement. Undergraduate research provides many benefits to students, including gains in student learning, for example, making use of primary literature, formulating research questions, logical and creative thinking, and personal gains, for example, increased ability to work independently, and greater tolerance for obstacles. The interplay between theory, as that provided through formal training in the classroom, and practice via mentored research experiences enhances both student learning and students' definition of career goals. Through undergraduate research, students' exposure and response to real-world problems and subsequent reflection upon the outcomes of their actions serve in their development and evolution of knowledge related to their interests. This involvement and importance of faculty mentorship of students during this experience is critical in student engagement and retention. The Research in Undergraduate Institutions RUI and Research Opportunity Awards ROA funding opportunities are two excellent examples of the commitment of the National Science Foundation in supporting research by faculty members at predominantly undergraduate institutions, PUIs. Today we will hear from two NSF program officers on these mechanisms for funding, and 6 RUI-supported exemplars from across the CSU to speak on their projects and more. Before we begin, I want to remind the audience to use the open chat box on their screens to type in their questions. Our speakers, when not presenting, will make every effort to respond in real time. So let's begin. It's with great pleasure to introduce Drs. Michelle Bushey and Rebecca Peebles, NSF Chemistry Program Officers, who will speak on developing successful proposals at primarily undergraduate institutions, NSF Insights on the RUI and MRI programs. Michelle and Rebecca, the floor is yours.
Good. All right. Well, thank you for inviting us here today. We're really excited to speak to you, and I hope that you find this to be useful.
Thanks, Michelle. Thanks, Rebecca, for a very informative talk and lots of information. So our next speaker is Amy Furniss from Cal State East Bay. Her talk is entitled Enabling CSU Undergraduates the Opportunity to Provide Impactful Contributions to Very High Energy Astrophysics Research. Amy.
All right, thank you so much to the organizers for me to be able to have this opportunity to share with everybody about my program and kind of some lessons that I've learned in submitting one unsuccessful grant, and then the next year submitting one that was successful. So I'm not assuming everybody here is going to be an expert in very high energy astroparticle research, so I'm going to try not to dwell on that part of it. But what I've done is I've created a program that allows undergraduates to contribute to my specific field of research. So studying very high energy astroparticle physics, but specifically the cosmological fields between us and some of these astrophysical objects. So the intention of the program is to allow undergraduates to gain experience addressing some fundamental questions in this field, such as how much starlight has been formed since the beginning of the universe, how magnetic is our universe, how does energy flow in the vicinity of a supermassive black hole at the center of galaxies. So these questions are just naturally very exciting. So undergraduates are sometimes very excited to get involved in this program in the physics and astronomy fields, but I also have made room to involve computer science and computer engineer majors. So there's a little bit more breadth there. I've used my connections with other collaborations and other institutions in order to help me succeed in an RUI type program. And I'll talk a little bit more about that. The type of activities that my grant supports is really my own involvement in the field, but allowing students direct experience with the application of the scientific methods. So I know in the classroom and even in lab classes, some students are introduced and get to play with this concept, but it's only in these research kind of endeavors that you get to practice and see how hard or the actual application of the scientific method is. So they learn the background of the science, they get to form a hypothesis on their own, of course, with my help, and then they're able to take data, analyze that data, and interpret the results in terms of their initial hypothesis. So they get to go full circle in that scientific method, and I think students really enjoy that, to see it in a larger context. The students get to use the Veritas telescopes to observe these astrophysical gamma rays that we use in order to study the very high energy universe. And so while they're using these instruments, they get to hands-on experience with hardware, software, general astronomy detection methods. They get to travel to site, which is in Tucson, south of Tucson, Arizona, and take a shift for taking data every single year. And this allows them access to some cutting-edge technology that they wouldn't necessarily have access to just at Cal State East Bay. They also are trained in a lot of software and analysis practices involving troubleshooting. And I have a quote here. After every single trip that my undergraduates take to Arizona, I give them a survey to ask how things went, what they enjoyed, what could have been done better. And this was a quote from one of our undergrads who graduated in 2018 and went to site in 2017. And just for completeness, I'll read it out. He says, "Veritas was the coolest research experience I've ever had, and I'm not just saying that because everyone working on it is cool. I think that the questions that arise from these blazars are fascinating because we still know so little, yet this project is dedicated to figuring out the questions step by step. It was fun to see physicists solve problems when the software was malfunctioning or when hardware was acting up, because it showed me that the greatest skill to learn is the ability to think about ways to solve a problem." And I think this is a really important part because we're not just training students to go into research later on, but we're training students to take on real world problems, whether that be in research, whether that be in industry or in a teaching career. And so being able to have them see that in action, I think, can make a large impact. So I won't dwell too much on the specific activities in terms of programming, but they are having access both to the hardware, so hands-on kind of stuff, and the software, as well as interfacing with the broader community through web-based resources and creating and maintaining those web-based resources in the context of multi-messenger astrophysics. But a big important component of this program is allowing students to own their own research and report their results out to the community. So you can start small and you can just have them report in group meetings and collaboration meetings. and then have them also travel to regional conferences to share the process and the results, and eventually contribute to peer-reviewed authorship or papers. I won't dwell on the specifics of the gamma ray astrophysics results, but my program has had a lot of success due to the financial support provided by the NSF RUI proposal. Not only does it support me to continue my research in my field of expertise, but it also provides student support, financial student support for them to be involved in the lab. And I think that this is good. At least many of our students struggle in maintaining a job outside of school, and it's very nice to be able to bring them in and provide some support while they're actually learning physics in the real world context. It also provides a lot of travel support to get down to the base camp where the telescopes are, as well as support for publications and regional conferences. Every single year, I have between 5 to 8 students that are involved in my group, and admittedly, some of these students are repeat students. Maybe they were sophomores and they continue on as juniors and seniors. But over the 3 years of my program, I've involved 14 total students, and these students have contributed to 8 publications, with 3 of those papers being significant contributions with authorship, with student authors. I think here the most important aspect is some lessons learned, and I would like to reiterate everything that was stated by the NSF experts that we had speaking before me. Give yourself ample time. 4 to 6 months really is a realistic thing in order to start thinking about where you might apply and the specifics of the program. You can start by asking yourself questions and answering those questions. So like what the program might be in terms of smaller projects, how those smaller projects might support an overarching goal, how many students do you want to involve, and what is the timeline of your program. And I think it's very nice for reviewers to have a visual of this, because they are going to be inundated with many proposals with many, many pages. And so if you can communicate the timeline and the organization of your program succinctly, it's very helpful. So I actually include here on the right-hand side of my slide the figure that I've shown, where I have 4 sub-projects, and I've described what these 4 sub-projects are in the caption, but as well as in great detail within the text of the proposal. And then for each sub-project, there's an observation, analysis, and interpretation component, potentially. And then I give years at which either myself as the PI or the undergrads would be involved. So for example, for sub-project A, the first year and second year, the undergraduate and the PI, myself, will be involved in collecting observations. Then for 3 years, that's the sub 1, 2, and 3, the undergraduate will complete the analysis of the observations that were taken. And on the 3rd year, the undergraduate or undergraduates will work with me in order to interpret the results. And you can see this kind of breakdown in all of the different sub-projects. To continue on with lessons learned, again, I'm reiterating that come up with very specific and small-scale examples of how you can create a project for an undergraduate student without overwhelming them. But these problems are complicated, as we all know, and so it's useful to pair students on projects so that they can kind of motivate each other, lean on each other, and work together on these projects, as well as create a get started protocol so you don't have to reinvent the wheel every single time you bring on a new student. Something like creating a shared drive and a checklist or something like that, so you can just hand this information to the student would be well worth your time. Continue to build on the peer mentorship opportunities that your project will naturally lead to, where you have experienced students working with new students, and highlight the skills that they're acquiring, both in your grant as well as to the students that are working with you, that they are beyond just the academic research scope, and that if any career path is going to be beneficial, these skills that they're going to be learning is going to be beneficial to any career path. Draw support on your collaboration or multi-institution collaborations like I've done with UC Santa Cruz. And within the paper or within the proposal, I would say give equal weighting to the importance of the grant to your own research, but also to the experience that the undergraduates will have by being involved in that research. So my next steps are I submitted another RUI grant. I will continue to build on the mentorship ladder, even extending it to students who have graduated and moved on from their undergraduate degrees and see where they go. Some will go into teaching, some will go into graduate school, some will go into industry, and to continue to work building the collaborative kind of connections with other institutions. The last thing that I really wanted to start concentrating on is dedicating a lot of time and resources to large collaborations, creating a type of playbook so that they are able to support, train, and invite undergraduates from many different backgrounds to be successful by being involved in their kind of in the kind of research that collaboration may be partaking in. So I'm short on time, so I'll be very brief with my summary. This NSF RUI proposal, it's a very good opportunity. I encourage everybody to take a peek at it and try to apply for it. And to build on collaborative partnerships outside of just the CSU system. There's a lot of institutions around that are working on similar questions, and you can benefit from those efforts as well. So I appreciate your time, and I'm happy to answer any questions if there are any.
Thanks, Amy, for a great talk. And I think you certainly hit home with the a focus on trying to build collaborative partnerships outside the CSU, which I found is very integral to faculty success, to not only count on and focus on one's institution and not only within the CSU, but also try to branch out to other campuses as well as to industry too. We have a question here. Which kind of follows along those lines. How do you formalize collaborations with other institutions with respect to your NSF grant?
That's an excellent question. There is a letter of support mechanism that is going to be in that very long pre-bedtime reading that was mentioned previously. Recommendation, so it is not an opportunity for somebody who you plan to work with to list your potential for success, but instead to just say, yes, I will work with this individual, and to include very specific ways at which that institution is going to collaborate with you within the proposal. So that's kind of formally within the proposal. And then I would say that outside of that, to have regular meetings with a collaborator where the undergraduates are able to join and communicate with those collaborators as often as possible will give them, it'll extend their view of what research really is.
Great. Thank you, Amy. And thank you for participating today and for a great talk. It certainly was a pleasure getting to know you. And certainly, I'm sure your students think the same thing. So thank you.
Thank you.
Our next speaker is John Goeltz from CSU Monterey Bay. And his talk is entitled Writing a Successful NSF RUI Grant Proposal When Your Campus Doesn't Offer a Major in Your Discipline. John, the floor is yours.
Thanks very much. Thanks for the introduction. Thanks to all the organizers, and good morning to everyone in California, and good afternoon to any of the NSF participants who are still here. I'm John Goeltz. I'm a chemist at California State University, Monterey Bay, here in the very center of the coast. I like to begin by invoking the observation that we've all got problems, and this is true in pretty much every domain of life. And I came across this, well, not that specifically, that I learned early, but I came across a way of thinking about this in an audiobook that I listened to. I go sort of outside my domain on the commute. And so I listened to a book by a Harvard Business School professor called The Innovator Solution. And one of the big takeaways from this book is that if you want to be successful they're thinking largely about business ventures, but I think it applies elsewhere. If you want to be successful, you should offer people a solution to a problem they are already trying to solve. If you're trying to sell someone a product or a service for a problem they're not trying to solve, you're going to have a hard time. And I've thought about this in terms of teaching, where teaching lower division chemistry to non-majors, we can offer lots of things to help them learn chemistry. That may not be the problem they're trying to solve. Here we'll talk about it in a research context. So my lab at Cal State Monterey Bay is made up entirely of undergrads. Okay, so we do research on batteries, but I spent 3 years in industry before coming to academia working on batteries, so quite a bit of our work is in energy. I have between 4 and 15 undergraduates at any given time. I've now sent 2 undergrads to chem PhD programs, despite us not having a major in chemistry, and we're a mainstay at American Chemical Society national meetings, all supported by National Science Foundation, RUI. So behave now. So active chemistry for safer and faster charging batteries is what I'll talk about today. Fast charging of lithium-ion batteries is a pretty easy way to make your broader impacts clear. So this is a charging curve for a Tesla battery. I won't belabor the details, but suffice it to say, you start out charging very, very quickly, and then as you get close to 100%, you have to slow down. And you do this to preserve the lifetime. If you keep charging quickly, which you can see there's reports of batteries that will do this now, you can charge it very, very quickly, but you do damage, you lose lifetime. If anyone is like me, you have several old laptops that are basically now desktops because the batteries won't store charge anymore. This is what will happen if you charge too quickly or too hot. The way we quantify broader impacts, or I quantify broader impacts for this proposal, is to say if we could charge at the same rate the whole time, you could save 45 minutes every time you charge. So we've still all got problems, and the way we solve this problem is with active battery fluid. So I'm a chemist, and we apply chemistry to what is otherwise largely an engineering problem. Okay. Since not everyone in the audience is a chemist, I won't, again, this too, I won't belabor, but we take 2 off-the-shelf chemicals. This is choline chloride, which is added to chicken feed, among many other things. And this is urea, which is used for lots of things. And 2 pretty high melting compounds, one organic, well, I guess technically not organic, but anyway, a small molecule, and then a salt. And these melt above 100 degrees C. If you mix them together in a 2-to-1 ratio, they make a new complex that melts at 12 Celsius. So that's below room temperature. Next, I've got a couple of videos, and these are, there we go. These make for really nice, engaging materials. It's very easy to get undergraduates or any audience engaged in these things because they're visually striking, right? You take 2 solids and you combine them together and you get a liquid. So that's what I've got here. The video on the left happens over the course of about an hour. Well, we don't have that long, so I've sped it up. So this is taking 2 moles of urea, 1 mole of choline chloride, 2 materials that melt above 100 Celsius, and simply mixing them, no heating. And you'll see I kind of get in there with a spatula at a couple of points to get it mixed up. But if you're patient, you can demonstrate to students, or they can do it themselves, of course, that 2 relatively low toxicity chemicals combine together, and they start as solids, but they create a new chemical that is, it's tempting to call it a mixture, but it's actually not. It's a new pure chemical, which is one of the things that's kind of neat about it. So that is the slow process here at the right. It's a little bit hard to see, but it's a clear liquid at the bottom. It's quite viscous, kind of like honey, maybe a little less viscous at room temp, but it stirs quite cleanly. So it offers the opportunity for a little bit of cognitive dissonance. It's just kind of neat, which is useful in both engaging undergrads and the general public. So I applied for I applied twice before I got a proposal. I think I know how to stop the autoplay now. So I took the structure from my advisor's proposals, which I was lucky enough to work with a distinguished professor at UCSD, well-funded, who, beyond all the support that he was able to provide for us, let us help on the NSF renewals and really see not the entire process, but a large part of the process. So we didn't work with sponsored programs as graduate students, but we worked with all the different components of the proposal itself. So this was good. I already had somewhere to start from. My overall plan for writing the proposal, not for what the research was, but for the proposal itself, is to line up all the pieces I needed and just do as good of a job as I could. I said, all right, this is how many months I have left until it's due. This is how well we're going to, this is the time I have. And then we had preliminary data that I had collected with some undergrads we had presented, but we didn't have any accepted publications yet. Okay. Rejected. Happens. So the direct feedback I got from the reviewers in the panel was that the proposal is unclear. The analysis of data was superficial, which admittedly I'm cherry picking some of the reviews, but these are the things that I tried to figure out how to deal with. And the concept that aiming to train underrepresented minority students is really good, but I didn't present a clear plan to do that. Okay. So I was lucky enough to get some time with a grant writing consultant from supported by the Chancellor's Office, and they helped me interpret this as the proposal is unclear. It doesn't necessarily mean that the writing was bad, but that the reviewers didn't get their heads around it. As Amy mentioned in her talk, the reviewers are reading lots and lots of proposals. And as the consultant I spoke with mentioned, you need to think about them as writing it after the 40th or 50th, or reading it after the 40th or 50th hour of work. So not only are they reading many proposals, they're doing it on top of their jobs, right? The analysis of data is superficial. This is kind of subjective, but once it's been peer reviewed, I mean, you can publish superficially analyzed data, but it just gains a different level of respect in the reader's eyes. And with respect to training undergraduate students, no one can say you're not going to do it, but they can't point to anything that's good in your proposal if you don't give them something to point to. So what it did was something that a couple of things that Amy alluded to, which is great. Basically try to put everything the reviewer needs to take away in a table or a figure. And you're going to describe it in greater detail, like she mentioned, but she showed the chart of the, who's going to do what in an abbreviated sense. To get publications, I competed for a couple of intramural on-campus mini grants to get some non-capital equipment that my startup wouldn't cover, so we could publish in some pretty good chemistry journals. With regard to training, the proposal that was successful that I wrote after this specifically included financial support for other experts on campus, to admitting I can mentor students in writing, but it's not what I do for a living, right? It's part of what I do. There is someone on campus who that is what she does for a living. So I included a couple of days of support for her and an assessment specialist. And this is good in terms of execution of the grant, for sure. It's also good in terms of a reviewer perspective because it gives them something to talk about, to say, yes, this person has a plan and here it is. Okay, we'll look through the animations here. Now we're both working on that. So this is a bit of an eye chart as the industry expression goes. I did a very, very detailed work plan and breakdown, 3 pages, landscape mode. And one reviewer said, this is too much detail. Don't do this. Do something simpler, more abstracted, like a Gantt chart instead, which I think I will do in the future. However, the grant was funded. So the tabulation of this worked. It became clear that I had a plan, that I knew who was going to do what. So I sort of did overkill on the level of detail here, but it worked. And I think I know how to meet that in the middle next time. Okay, so again, how do you get these good publications before funding? My startup was a little bit lower than some of the others, and I'm a chemist at a school that doesn't have chemistry, so we don't have instrumentation, so to speak. So I recruited hard. I taught lower division chemistry, which meant I had to teach a lot of students, but I got to steal all the best ones before they got to scuba and playing with sea lions and stuff like that. We'll come make them melt salts at room temperature instead. One piece of advice that was really useful was do not be afraid as a faculty member to be first author to get the papers out the door. I'm very much mentoring focused and came from a lab where the researcher writes the paper, but it just isn't always going to work on the time frame that our undergraduates have. I think it was Frank mentioned earlier, the students are kind of almost seasonal, right? They come and they go and they work part-time most of the time. Compete, do not be afraid to go grab the intramural mini grants if your campus offers them, or if the Chancellor's Office does, or if there's an affinity group like COAST or the ARI or any of those, go get them. And don't just Gantt chart the work. That is, so if you're not familiar with this, is sort of business world organizational project management tool for who's going to do what and when. Do that for writing the proposal. I did this for the second one, and I said, all right, how many hours is it going to take me to write a good project description? The RUI impact statement, as a couple of people mentioned, can really matter here. How long is it going to take me to do this? And then I said, well, I'm going to need to get up at 4:45 from now until then to do this. And that's what I did. And it came out a lot better for it, rather than just sort of letting the job expand to fit the time I had. Okay. With that, I'll thank all of you. There are many, many, many undergraduates supported by NSF in this work, and here's just a handful of them. Some of my students are talented graphic designers, so they took Goeltz and put an electron in the middle of it because we do electrochemistry, and I'm a bit of a tropical drink fan, so they teakified my logo there as well for a cyclic voltammogram on the back. So I thank NSF very much for the support and all the people who helped me get there, and then the organizers today for letting me share some of what worked and didn't work for me with you.
Thanks, John, for a great talk. And I like the CV there on the picture. Okay, you're a man after my own heart, being a kind of a pseudo electrochemist myself. So here's a question for you. What is your approach to your goal of having undergraduates write and be first author on peer-reviewed publications?
I like to provide everyone with a paper by George Whitesides published in Advanced Materials, and I forget the title, but if you Google search George Whitesides writing a paper, you'll find it, and it's open access. It's actually it's presented as a mechanism for outlining writing a paper. It's actually, I think, a way for outlining a research project in its entirety. So I try to give them that as soon as they join the lab. And then I try to work with them. And, almost everyone starts with, oh, well, write the experimental section and we'll go from there. But as I mentioned in the talk, leaning very heavily on the on-campus writing support. Our campus is lucky enough to have a research supporting office that includes a writing tutor. And she's generally happy to work with our students anyway, but putting her explicitly in the grant to support them has been just super helpful in getting the papers from where they start to where they need to be, remembering that pretty much every time an undergrad is writing a paper, it's likely to be their first time.
Well, you certainly learned from a pro. I was a postdoc with George a long time ago. I won't mention that year because everybody will know how old I am. But one of the first things that George gave me was how to write a paper. That article, actually, this will show a little bit. It was shortly after it had been come into publication. And so he just forwarded a hard copy of the printed manuscript to me, and I still have that to this day, many years later, and I would actually use that with all my undergraduate students. For years, I had them write a draft of the work that they put together, and as you probably are aware, George had everybody just provide outlines at the onset. And that's how I wrote my first paper with George. And I continually do the same thing. Another thing that I never did, other than probably my first 3 or 4 years as a faculty, I don't remember the last time I was first author on any of my papers after it's probably been decades since I was first author, because I found out that there's probably not any more time that Frank Gomez needs to be a first author on papers. The students need it probably more than I. So, but certainly, thanks for your talk, and certainly a lot of information for faculty and new faculty to take to the bank. So thanks for coming on today.
Thanks very much. I'll just flag that it looks like someone put a direct link to that paper in the chat. But thanks, everybody.
Great. Our next speaker is Melanie Michalak from Humboldt State University, and her talk is entitled Evaluating Crustal Deformation in Southern Cascadia, a Collaborative Approach. And I'm sorry, it's Crustal.
Thank you. Thank you, Frank, for that introduction. I'm really excited today to tell you about our collaborative project. It's a 3-year project funded by the NSF EAR Tectonics program. So I'm going to start by giving you a general summary of the research importance, and then explain our very purposeful approach in our collaboration, and then I'll demonstrate how we wove the broader impacts piece into the project. So as Californians, I imagine that most of you are familiar with the San Andreas Fault Zone and the seismic risk associated with it. The San Andreas Fault terminates in Humboldt County on the coast and transitions to the Cascadia subduction zone marked in this image. HSU is denoted by the gold star, and our education partner, Hoopa Valley Elementary School, is about 50 miles east of HSU in the heart of the Klamath Mountains, which is the general region of study. So broadly speaking, we're interested in the Cascadia subduction zone for one main reason. It presents a major seismic hazard to the entire Pacific Northwest region. So the image on the right is a modeled shake map from USGS, where orange represents very strong shaking and blue is light shaking, given a magnitude 9 earthquake on Cascadia. So as a quick note, a magnitude 9 earthquake is about 1,000 times stronger than the 1989 Loma Prieta earthquake that occurred in Northern California. So compared to the San Andreas fault, we know much less about how Cascadia behaves, which is largely because it last ruptured 321 years ago before seismic instruments. And in fact, scientists didn't really understand Cascadia's seismic risk until the 1980s, when stories about earthquakes and tsunami from coastal indigenous peoples were put into context with the geologic record. So as geologists, to address seismic potential, we really need to understand how the two tectonic plates interact. And we really need to understand how these two plates interacting accumulate strain over time. And we're interested in time decadal scales, so human time scales, or earthquake cycle time scales, and then also millions of years, so geologic time. There are a few different ways to quantify crustal deformation. For example, processing data acquired from GPS instrumentation, as well as using techniques like mineral geochronology, which I'm going to address in a few slides. But first, I wanted to give you a general architecture of the collaboration, and I hope this is going to be relevant to everyone listening, not just people interested in applying to the Tectonics program. So this was a grant submitted collaboratively by 3 institutions. Those institutions are Penn State, Oregon State, and HSU, which is the RUI, and the other 2 are not. So we proposed this collaboration because each of the PIs from these 3 institutions represented a different subfield of geology: geodynamics, geomorphology, and tectonics geochronology. So we marketed our proposal as needing all 3 of these subfields to address crustal deformation on those different timescales I just talked about. And our 4th partner was the community. And this was part of our broader impacts part. So like many NSF proposals, we chose an education partner, but it was also selected purposefully. We chose 6th grade because 6th graders in California have earth science as part of their state mandated curriculum. And we partnered with Hoopa Valley Elementary School because their school is located in the heart of the field area we propose to access on native Hoopa land and within the Hoopa Valley Indian Reservation. So we conducted several visits to Hoopa Valley Elementary and arranged for the 6th graders to travel to us, which is about a 90-minute bus ride through the rolling mountains. And HSU is the major institution that serves this entire rural area. All right, so some of these details that I wanted to share with you, the 3 subfields of geology. We have the 6th graders from Hoopa Valley Elementary, and as you can see, the RUI, the Humboldt State, the RUI, we could support many more undergraduates and classes than the more traditional non-RUI big R1 institutions can support, because we can go a little farther with the money that we have. So we also plan for yearly meetings with all the institutions together. When during the pandemic, we substituted this annual yearly in-person meeting for monthly Zoom meetings, which were actually surprisingly successful and a lot of fun. So within the research group at HSU, one piece of the proposal involved evaluating crustal deformation on million-year timescales. And to do this, we use a technique called thermochronology, which uses tiny little minerals, hundreds of microns in length, to measure their isotopes of uranium, thorium, and helium as a way to determine when they cooled. And rocks cool as they come to the surface of Earth. So anyway, to do this at HSU, we had to acquire a specialized microscope. And this cost about $35,000, and we did not have it, and my startup could not cover it. So having that microscope at HSU was a really important piece of this proposal, because that means that undergraduates could access it and could actively participate in the research. So we wrote in the acquisition of the microscope into the grant. Another aspect of the research at an RUI institution is multiple levels of student engagement. For example, I taught a class at HSU, which is pictured in this image on the lower right, where we led a weekend field trip to hike up the landscape and collect rocks for the thermochronology analysis that I just talked about. So some students were involved just in this weekend trip. Others spent hours processing samples in the lab. A handful of students ended up doing mineral picking with the microscope, which is actually just behind me in my screen today. And some students ended up doing the dating method and carrying on research as senior theses and master's theses. So some students spent a couple of days, other students spent multiple semesters. And that's what I'm talking about, multiple levels of student engagement based on what the student is interested in and what they have time for. So to summarize the research activities so far, and I want to highlight this multiple levels of student engagement. We have a class field trip to collect samples. We have master's students training bachelor students. And then we have students giving first author presentations and publications. And then finally, we also have students traveling to national laboratories. We use the laboratory at University of Arizona, and then also University of Colorado at Boulder. And so that those students could learn the best practices and acquire publishable high quality data. Our activities on the education side, as I mentioned before, was establishing Hoopa Valley Elementary as a partner during the proposal writing. And this is really important. We met with the teachers before our visits to their classrooms, and we asked them, what do you want help with in terms of teaching or science? So they gave us a list of topics, and the bachelor's and master's students at HSU designed the activities. We traveled to Hoopa Valley Elementary, and we paid for bus travel for Hoopa Valley to come to us. So importantly, the sixth grade teachers put in time, thought, and creativity into working with us. So we wrote a stipend to honor their time into the grant. And when working with the teachers, they specifically told us, our students do not like state standardized testing. So we don't want you to test them with any kind of, multiple choice exam or anything like that. So assessing what we could do for them was required a little more creativity. So what we did was we asked them to write on note cards before we started working with them. What do you think geology is? What does a geologist do? And here were their responses prior to working with us. And then, so you can see that this is a word cloud. And what this shows is that the larger letters indicate more frequent responses from the students. So they understood that geology was studying rocks and earth and minerals, and a lot of them didn't know. And then after working with them for a school year, the responses got a lot more complex. And one thing to note is that they included a lot more active verbs like make, identify, study, teach, look, etc. So briefly, to summarize the results from HSU, we saw sixth graders demonstrate higher level of understanding about geology and what a geologist does. From the science side, we're finding evidence for crustal deformation and upper plate faults within southern Cascadia that really require us to think of the Klamath Mountains as more of a complex crustal feature than previously recognized. And then finally, there's intangibles, right? Due to our collaborative approach, we see trust, partnership, mentoring, network as important results as well. So if I had to narrow down the 5 major lessons, like others have said, and I echo, resubmitting an unsuccessful proposal and incorporating the negative reviews are really important. And also to address the literature that's come out in the last year or two since you've applied is really important. And reframing that proposal to incorporate all of these aspects. The broader impacts, we tried to view not as just an add-on, but actually an integral part of the work, place-based work. Students are incorporated at every level. And then we also included a plan for mentorship, right? We have senior PIs, a junior PI, myself, graduate students, and undergraduates. And then finally, like John, I also worked with a CSU Chancellor's Office sponsored a mentor for the writing portion. And I got, I think, the one-liner that I'll always remember, think of a proposal not as a proposal, but a marketing document. And at the time, I sort of groaned when I heard this, but it's actually really great advice because timelines, work plans, those kinds of details, you're marketing yourself as someone able to do all of these things and deliver. And that's what the reviewers want to see. Okay, so a couple of challenges that came up that I wish I had known when I had applied for this grant. Student turnover rate can be faster than the publication rate. So one solution is to plan, as a PI, plan a reduced teaching load or sabbatical at a key time in the grant cycle. Another challenge with student products are not in a central location. So really work with your students to understand Google Drive or Dropbox or some other method to organize all the work. And then of course the pandemic was a challenge. So we did a lot of Zoom meetings. So in summary, you can submit an RUI collaboratively with non-RUI institutions. There are pros and cons to this. And you can write in acquisition of key instrumentation within a certain price tag if needed to involve those students. Remember multiple levels of student involvement. And then we really viewed our broader impacts as a partnership and not simply outreach. Thank you.
Thanks, Melanie, for a great talk. You have a question here. What are some best practices for keeping a partnership such as the one that you have with Hoopa Valley Elementary strong throughout the 3-year grant and beyond?
Thank you for that question. We found that working with an elementary school, especially in a rural area, took a lot of time on our end and their end too. So that's why it was really important to value their time and pay them as part of the grant. A couple of approaches we used to make initial contact. We drove to the school. Teachers, if you've ever known any elementary school teachers, they are so busy and they're too busy for emails and calls. So to start that trusting relationship, we found was best in person, which I recognize after the pandemic makes this a lot more difficult. So as we transition to kind of a new normal, we're exploring ways to keep the partnership going by mailing supply kits or by incorporating the work into a capstone class at HSU. So that's another creative approach for some of these proposals. Use the classes that you already teach to try to incorporate the work of the proposal into your already large teaching load.
Great, thanks. Yes, my mom taught Head Start for 25 years and my dad taught high school for 30 years. So I kind of have a gauge as to how busy our pre-K through 12 teachers all the jobs that they have and all the different hats that they wear. So certainly thanks for all the work that you're doing and working with Hoopa Valley Elementary. So thanks for being here with us today and great talk. Okay.
Thank you.
Our next speaker is Wang from Fresno State University, and his talk is entitled Low Power Bulldog Moat Design for Wireless Sensor Networks. Nan?
Okay, yeah, thank you,
Nan.
Frank, and for the introduction, and thanks to the organizers. Okay, so yeah, again, this is Dr. Nan Wang from the Department of Electrical and Computer Engineering at Fresno State. And today I will briefly introduce our low-power Bulldog modes design project supported by the NSF NETS grant. Okay. I'm currently leading a cyber-physical system research group at the Fresno State, and we are carrying out some research projects, including wireless sensor network, machine learning, image processing, embedded system, new energy technologies. And Fresno is located in the Central Valley, and we have a lot of research opportunities in the field of Exxon's smart grid and WSN and so on. And we are also close to many high-tech and agriculture companies in the Central Valley and even San Jose area. So we actually received the NSF grant in August 2018. I will talk about that later. Okay, all right. So to start the proposal of this project, and we actually group the ideas actually in early 2017, and we are thinking about the wide application of WSN and the features of low power operation requirements. So we are thinking about to combine the low power design technologies and the new energy harvesting technology together, so to form this project. So the goal is kind of like a clear and cutting edge. And in the proposal, we emphasized students, from the underrepresented group, especially for the undergraduate students. And we try to bring real-world application and research experience to them. And most of them actually are first-generation college student from the family, and yes, and so. And also we emphasized, like mentioned, multidisciplinary collaboration between faculty in the Fresno, and we set a realistic goals with a reasonable budget. Also, we need have a clear research and evaluation plan. These are all key facts in the proposal. And of course, in the project, we try to involve undergraduate students especially, and we try to present the project in our courses and reach out to the students, like especially the good students who are maybe interested, and involve them in the project earlier. Okay. And I'm the PI and in charge of system integration and testing, communication protocol, and the low power technique design. Dr. Na is the co-PI in charge of the new energy design. To disseminate result of the project, we actually have a lot of ways, and we try to present this project in many different places, like in the courses, in the open houses, workshop, and orientation and conferences. So I will mention that again. And the project actually involved more than 15 graduate students and 20 undergraduate students in the last 2 years, and most of which are from underrepresented student groups. Wireless sensor network consists of many sensor nodes spread in a certain area to collect information around them, and each of the node can sense, can sample the environment, and they can pass the data through a selected way to the sink, and then to the internet cloud storage by the end to the users. So this is pretty much a very interesting technology, and emerged like 10 or 20 years ago, but still under a very high level research. There are 5 basically design layers for WSN design, and at the beginning we proposed to apply low power techniques on each of the layers, and mainly we proposed to develop newer technologies or algorithms, or we improve the existing algorithms. This is the main idea, but I do not have enough time to break it down. So yeah, but you can find all the information on our website. And the project activities, we try to present the project in many places, like I said, and I delivered keynote speaking presentation in several IEEE conferences in USA, Canada, and China, and my co-PI, Dr. Na, also presented like locally and internationally, and we also hosted a workshop. So during the pandemic, and we allow our faculty and student research assistants present their project in front of all these Fresno State faculty and students. And we also participate in all kinds of open houses and orientations. And in the last 2 years, we published 13 IEEE international journal and conference papers on this project only. Also, several of my undergraduate students won Best Paper Award in IEEE conferences, also the Best Presentation Sessions. So the projects we carried out, including the protocol design, the gateway design, sampling and processing, and also the energy harvesting projects. And also, like I said, we try to even reach out to the high school students to inspire them to select engineering major and to attend like CSU campuses. And we also, went to all different kind of like conferences and to talk about our project. And the student actually did a good job on the research. And other than the papers we published on this project, we supported around like 15 senior design projects and final projects. And several students found job in these big companies in the San Jose, Sacramento area, and including Intel, Synopsys, and Lockheed Martin. One student received 5 job offers before graduation. I think he went to Lockheed Martin. He's the first generation college student in the family, and I even brought him to China to attend a conference. And also we establish many collaborations and for future projects. Also on the left side is that the blackboard is designed by the electrical students for the energy harvesting project, and on the right side is the baseboard for the we call it like a Bulldog because it's our motto. So Bulldog moat project. So this is the baseboard, and we are testing both of the systems and try to make it perfect. Lessons learned. A lot of presenter already talk about the lesson learned from writing the proposal, and this is actually from my project. So never underestimate the potential of your undergraduate students. I actually was surprised by some of my undergraduate students, and they are actually sometimes they are actually very aggressive, to learn new technology and can provide a lot of help, and also involve undergraduate students in your research as early as you can. Always start from a smaller, simple projects to encourage the students and give them enough training before they are started, and connect the student to the industry. Like we have like 3 students working for a same location of Intel company. So this is a very important lessons we learned. And next, we have finished most of the research activities, and we are ready to make the final PCBs and start to test the whole system. And several weeks back, and a couple of faculty in Fresno State invited me to join their another proposal to CSU transportation. They try to monitor the pollution level in the Fresno area, and we can actually use our dedicated designed Bulldog mode in this real world application. So this is a very good chance, and we also try to submit other proposals. So pretty much, since the time limited, so I can just give a brief introduction, and this project has been successfully carried out. This is the 3rd year, and we finish it very soon, and many students were benefited from the project, and we also will test it in the real world wireless sense network application. As I said, the air quality monitoring project. This is will be another project we will conduct. Okay, thank you. This will be it for me.
Great. Thanks, Nan, for a very interesting talk. We have one question here. How did your group disseminate results from your project?
Sure. Oh, thank you very much for the question. Actually, to disseminate the project, we designed to have several ways. And we created a website for the project linked to our college website, and based on the requirement from the NSF director, and we pretty much put all the information of the project and the result, tutorial, progresses, and breaking news, and whatever materials on the website. So open to everybody to visit. And next, we try to disseminate the result of the project in different locations, like places, like I said, conferences, open houses, workshop, even today in this webcasting. And also through we disseminate the result through publication. As I mentioned, so we published 13 in last 2 years, and I think we have 3 to 4 submitted papers already. Okay, pretty much this is our basic plan. Yeah.
Great, thanks, Nan. Thanks for participating, and it's great to see you again. Thanks.
Thank
Great.
you. Yeah, thank you. See you.
Our next speaker is Rosemary Sherriff of Humboldt State University, and her talk is called Diverse Conifer Responses to Drought in Northern California. Rosemary.
Thank you, Frank, and thanks to all of you attendees and also the presenters. I've learned a lot. I first want to just acknowledge my co-investigator, Dr. Lucy Krahulis, who's been key in this writing the proposal and also for the project, the duration of the project so far. And then we've also had a number of different
Let's see here. Sorry about that. In an effort to turn off one of the mics, I accidentally moved Melanie into participant mode. So, or Rosemary, excuse me. So, Rosemary, if you could please activate your webcam and mic one more time, I apologize. And I'll hand it back over to you to continue on. Thank you very much.
Okay, got it. Yep. So I don't know where I left off, but anyways, I wanted to acknowledge my collaborators, and I'll bring them into the discussion later on also. Secondly, I just first want to acknowledge that the land in which I live, where I work, and then also the locations of this study sit on traditional, ancestral, and present homelands of many indigenous nations and people. Well, the context of the proposal, which is on conifer responses to drought, was the recent drought from roughly 2012 through 2016. And this is just a diagram illustrating the severity of that drought, which in California, across California, we're all very well aware of, that impacted impacted Californians in many different ways. So in my line of research, I'm really focused in thinking about forest ecology. So the graph or the map on the right shows a couple of different things. The colors in general show you the distribution of where forest systems are in California. And then the yellow through red represent the severity of tree mortality associated with the California drought. And the graph on the right shows the numbers are probably very small, but the first bar shows during the drought. And you can see that the mortality actually was a little bit lagged. So 2018, for example, had high amounts of mortality. Another, which is the year that we wrote the proposal. Another thing I want to talk about the map is that you can see that most of our forests are actually in Northern California. And the majority of research in terms of thinking about tree mortality has come from southern and central Sierras, which has been hit hardest in terms of tree mortality. But there's actually a kind of a gap and a lack of knowledge and drought response of our forests in Northern California, which set up sort of the context of this proposal. So the primary research objective was to look at drought response of conifer species across different habitats in this area that's represented by a box. There are over 30 conifers in Northern California, so it's one of the most biodiverse areas in the nation. And we focused only on 6 based on thinking logistics and the amount of funding and so on. But those species were important for a few reasons. 1, 2 of them were in their southern range distribution. 2 were endemic or locally only existent in Northern California. And then 2 were much more widespread. So looking at different types of conifer species. The second primary objective, like a lot of the other presenters have discussed, was a key component of our proposal was really highlighting that we were looking to promote scientific development and STEM research and mentorship to diverse undergraduate and graduate students at Humboldt State. What I'd like to do now is use a short video that highlights one of our outreach mechanisms, which is this video and among other things, and I'll start it in a second. But it also highlights our project, but it also highlights the importance of the diverse students that have been working on the project. It was developed by our collaborator, Michael Kaufman, who runs Backcountry Press, but he's also a science educator. So he's used this video and another one to share with K through 12 students in our region.
This National Science Foundation project is examining how competition, species, and habitat interact to influence conifer tree responses to drought. Since 2010, over 52 million hectares of trees have died in California's forests due to climate change, drought, and drought-induced disturbances such as wildfire. Forest loss and wildfire trends have important implications for the health, safety, and well-being of communities in both urban and rural areas throughout the American West. The effects of how competition, species, and habitat interact geographically to influence tree responses to drought is being studied across 6 conifer species, including western hemlock, Shasta fir, western white pine, sugar pine, Sitka spruce, and the regionally endemic Brewer spruce. Focused in Northern California and Southern Oregon, the study will provide essential information about the potential impacts of ongoing drought to forest species in a biodiverse and culturally important region of the Pacific Northwest.
The goal of the project is to look at how different conifer species are responding to the recent California drought across different habitat types, so from really dry sites to really wet sites. And we're trying to understand how they respond to drought as an indicator of future potential droughts and climate change. Another factor that we're considering is how the competition around a tree with other trees at dry to wet sites impacts how a tree responds in terms of growth and carbon isotopes in the tree rings.
One of the major objectives of our project is to provide hands-on learning experience, work experience, professional development experience for our students. So last summer we hired 5 different students, and then this summer we have 10 different students that we've hired, and all of them are getting really amazing hands-on kind of real-world experience doing science out in nature, and so I think that's really cool. The majority of the students, and we have 10 students and 3 undergraduates out here today, most of them are either first generation or come from a background of underrepresented in terms of their experiences in science. And we also aim to give people new experiences. So most of our students have not had any forestry, not any plant ID, and we're out here to give them a leg up in those kinds of fields.
So when did you become interested in science?
I became interested in science from the beginning. I grew up in my mom's garden and spent my early years playing out there in the mud and with the bugs and learning how to grow plants. So I became interested in science because of my mother, who taught me how things grow and not to kill spiders or not to hurt anything. So that kind of helped me become an early ecologist, I guess.
Tell us about that tool you're holding.
This is an increment borer. This is how we gather the most important part of our data. We drill it into a tree and it allows us to count the tree rings without cutting the tree down. And right now it's stuck, so I'm using this custom tool to try to unstick it.
And what do tree rings tell you?
Tree rings tell you not only the age of the tree, but also how much it was able to grow during a particular year. So a good water year or a good growth year is going to be wider, have a wider ring than a drought year, which is kind of what we're studying, the difference between drought, or how trees responded to drought as opposed to like a wet or regular precipitation year.
How does your work make the world a better place?
My husband often asks me when I'm feeling stressed out with my job or overwhelmed, he's like, well, what would you rather be doing? And I'm like, nothing. This is my dream job. Like, this is the best thing that I can do with my time on the planet. I think we all need to work to feel like we're contributing to the space around us. And I think that studying nature is a really nice use of your time, basically. Like, we all have to do something, and I'd rather be studying plants and trying to understand them better because I feel like they're like a tonic for making me a better human. I'm happy to get to geek out on plants, and I think the more that we know about plants and that we can share our enthusiasm about plants and get people pumped on plants, I think that makes people better. And so that's probably helping the planet.
I was going to stop it there just because of time, if that's okay. I showed that video just to emphasize we aren't professional actors, and it was off the cuff and we didn't know the questions. And that was one of the first days in our second field season. But just to highlight the project, but also the diversity of student experiences, and then sort of humanizing the work that we're doing as faculty members, which is now this video and others are being used in the K through 12 system in our local schools. I want to focus the rest of the time focusing on some take-home points for success that's in some ways are the same and some differences between the other speakers. So one of the things that I found, our proposal was funded the first time around, which was remarkable. I think some of the reasons for that or key to success was the interdisciplinary collaboration between Lucy and I, and then our non-academic collaborators. Lucy and I bring different types of expertise, different writing skills. Management of the project has just been huge. We've worked really well as a team, and we hadn't worked together in this type of project before, so it's been very fortunate. Some other things that have also been highlighted, I can't emphasize enough that in our proposal, we wrote in that the students were going to be co-leading this project from the get-go. And that has definitely been an important component of our program. And we focus on students mentoring each other. We've been able to, in total, support 14 undergraduates, 4 master students, and a former master student of mine who's doing her PhD in NAU has been paid to help with some of the statistical, or giving advice for some of the statistical analysis that she had done that's very similar to some of what we're doing and help some of the master students. It provided enormous applied training, as I mentioned in the video, which most of these students didn't come in with any type of background in that. And then again, there's been a real focus on diversity. Nearly all of our students have come from underrepresented groups. Another thing that I think made our proposal successful is that we focused on not only just the broader implications as mentioned in some of the other presentations as an add-on or outreach, but we really focused on what ways can we make this useful in a variety of ways. So I have a list of different outreach activities in addition to standard research activities that we're carrying out. And we have done some of these, and then we're working on this over the next year. We're just finished the second of the third year. And my time is nearly out, but I'll just take a last couple seconds to say this pandemic has been just incredibly difficult for all of us, and certainly it made this project more difficult. So through, logistically getting everybody out into the field, the university was very helpful, logistics and a little bit of financial support. So I do want to say that in the event that uncertain circumstances come about, I would encourage people to ask their universities. All they would say is no or yes. And that's it. I'd take some questions if there's time. Thank you very much.
Thanks, Rosemary. Here's a question, and I know you alluded to this already, but briefly, why do you believe your proposal was funded? If you have any more points you would like to add to what you've already said.
Yeah, I think any NSF proposal has to have a strong scientific basis. And so, but a key thing, I think, and this is stemming from prior proposals that weren't funded or other funding that I've had. In this proposal, we really strongly emphasize the student component, and very specifically, not only in the RUI statement, but in the proposal itself, and mapped out the roles that they would play. And then the second part, as I mentioned in the presentation, is we really thought as deep as we could about broader implications and diversifying those. So that I do believe that that was a real stronger driver of why we had our proposal supported.
Great. Thanks, Rosemary, and for a very, very interesting talk. Our next speaker is, and last but not least, is Andres Martinez, and on an area that I'm certainly very interested in, research on paper. Andres, the floor is yours.
Thank you, Frank. Thank you for the invitation. Thanks to all the other speakers. I feel like I've already learned some good tips for my next proposal. So what I'm planning to do today is tell you a little bit about the NSF RUI project that I have going on and kind of my process writing that proposal, and hopefully add some tips of my own as we go through this. So just to frame this, my area of research is in the development of what we call point-of-care diagnostics. These are small portable devices you could use to test, to diagnose some kind of disease, and you could use them either at home, in the field, in a doctor's office. These devices got lots of attention with the recent epidemic, and they have the potential to really change the way healthcare is delivered around the world, from a more centralized model where if you don't feel well, you have to go to a hospital, to a more decentralized model where you could test yourself at home first before going to the hospital. And you can imagine that would have a huge impact for populations that don't live close to a central hospital. And specifically, my work is on this first picture on the slide of paper-based diagnostics. And the gist of this area of research is that we can take a piece of paper, pattern it with either a polymer or a wax to define what we call channels and test zones. And the channels can wick fluids by capillary action, and the test zones can contain reagents that can react with our sample and give us some kind of indication that whatever we're testing for is present. So these three pictures just give you a kind of this classic sequence of how this device might be used. We have our device, it's a piece of paper, it has 4 test zones, they have reagents dried on the device, and then to run the test, you apply your sample either by adding a drop of it onto the device or dipping it into a drop of the device as is shown. The sample wicks into the device, interacts with those reagents, and produces, in this case, a color change to indicate the presence of the things that you're testing for. In this case, it was glucose and protein. So when I was finishing up my graduate work, which is also in this area, my advisor gave me some good advice, which I took to heart, which was if I was planning to go and work at a primarily undergraduate institution, I should think about coming up with projects where you could run relatively simple experiments and yet still do high impact research. And he gave me the example of this scientist. I don't think he even told me the name, but he told me the story of a scientist who studied avalanches. He was at a PUI, and his students would basically make little piles of sand and videotape them, and then he would work with them on the data analysis and was very successful at doing this. But the basic tool that they used was this very simple setup. And so I tried to apply that as I started my own career. I applied 3 times unsuccessfully for NSF RUIs until I finally, the 4th time was charmed in my case. I got a proposal funded. And the things that I think were key to that successful proposal were that I looked for a compelling problem that I could try to solve. And again, changing the way healthcare is delivered and providing access to healthcare to a wider population, I think is a very compelling long-term application. And I looked at a specific problem within the field, and also that it could be addressed by studying some fundamental phenomena. So we could do some really basic science to address that problem. And so the problem that I aimed to solve was one that these types of devices, these paper devices, are very good for running what I call a single-step assay, in the sense that you add your sample to the device, it mixes with some reagents and produces some kind of signal. Now, the reality is most tests don't work that way. Most tests require multiple sequential steps. And so this cartoon just illustrates a very common type of test called an ELISA. This is how most diseases are diagnosed. And the point of this is just that it requires at least 3 sequential steps where you have to do incubations and wash steps before you can get your answer. And paper-based devices are not as good at doing this sort of test, at least in an automated way. We'd like to remove the user as much as possible from the process and have the device run the test automatically. And we thought we could address this problem by studying the fundamental phenomena of what's called evaporation-driven capillary flow. Now, this is how trees and plants get fluid into their leaves. And the idea is that as fluid evaporates from the leaves, that essentially pulls more fluid from the roots up through the plant and into those leaves to replenish that lost fluid. And that process is called evaporation-driven capillary flow. So the focus of the proposal was to study evaporation-driven capillary flow in paper-based channels, which is something that has not been done before, and try to harness these 2 types of capillary flow to produce diagnostic devices that could perform these assays that required multiple sequential steps. So the gist of our proposal was to study both traditional capillary wicking and evaporation-driven capillary flow. The difference between these two is simply whether your tube is dry or wet when you start the experiment. So in traditional capillary wicking, our tube is dry, and we watch the fluid wick into that channel or into that piece of paper. And in evaporation-driven capillary flow, we pre-fill the tube or the paper, we pre-wet the paper, and then add a fluid that has a colored dye in it just so we can track it and watch that fluid flow. So to actually implement this and what we proposed in the proposal, again, was to compare these two and study evaporation-driven capillary flow to essentially learn how it works, be able to model it, and ultimately be able to apply it to our to producing our diagnostic tests. That's kind of the end goal, but really the focus of the project was studying evaporation-driven capillary flow. So again, really focused on the basic science side of things. And the activities that would be involved, again, going back to my advisor's advice, were to focus on this really simple setup, really simple experimental setup. So we included an environmental chamber in our proposal. This is just a plastic box that allows you to control temperature and humidity. It felt like it was a bit of an expensive item to put on the proposal, but it was critical to the project. And like previous speakers have mentioned, you want to make sure you include the equipment that you're going to need to successfully carry out that project. That's going to be critical to a successful application. So we got our environmental chamber, and our setup essentially involved putting these paper channels into this box and videotaping the fluid as it wicked along these channels, either under traditional capillary flow conditions or evaporation-driven capillary flow conditions. So relatively simple experiment, and we could use the same setup to study all sorts of things, including the effects of different designs of the device on the evaporation-driven capillary flow. So we looked at things like, again, the difference between these 2 types of flow. This is the actual data we collected through the project. We can see they're different. They follow different. There's a different relationship between distance and time for these 2 types of flow. We proposed to look at things like the effect of the size of the evaporation zone. This is essentially the top of the tube and where the fluid is evaporating from. We hypothesized that the larger that zone gets, the faster the fluid would move, because we'd have more evaporation. That turned out to be true up to a limit. There's a limit in terms of how much fluid that tube can transport. And so at some point, if you make your evaporation zone any larger, it doesn't help. You're already at maximum flow rate. We also thought the shape of the evaporation zone might have some effect, but it didn't. And I think that makes sense to us now. You can change the shape. It doesn't matter as long as the surface area is held constant. These are just two examples of things that we looked at. We looked at all sorts of other things: the channel length, the temperature, the humidity, and again, all of these experiments rely on the same basic setup. And so we could have a team of students working on this. They could all come into the lab, even a couple of hours a week, and run one of these experiments and collect useful data. And when we were in the middle of this project, I had a spreadsheet with basically a list of experiments, and as students had time and availability, they'd come in and they'd just check an experiment off the list and run it. And that proved to be a very productive way of moving the project forward. The other thing that was, I think, important for this project is that all of these experiments could be done in parallel. They didn't depend on each other, and I think reviewers are especially wary of proposals where your future steps are highly dependent upon a successful initial experiment. That's usually seen as a bad thing, because if your initial experiment fails, well, your project's ruined. So really trying to focus on a project, on a proposal where you show multiple parallel paths, so that if one of those paths fails, well, that's unfortunate, but you still have all these other cool things that you can still work on, and the proposal and the project itself is not doomed at that stage. So that's something else to look out for and try to implement. We're still finishing up, we're wrapping up the project now. We're in our last year. We've learned a whole lot. It took us a lot longer to do things than we initially thought. And we're at the stage now where we're trying to, we've studied evaporation during capillary flow. We're trying to implement that into one of these, diagnostic tests that can actually do an assay that requires multiple steps. And this figure I actually included in the proposal. This is the only preliminary data I included, was this one figure. And I think it really, I'm only hypothesizing here, but I think it really supported the application and was key to it being successful. It just shows the idea that you can have fluid go in two directions and have these two different types of capillary flow: normal capillary flow and evaporation during capillary flow. I didn't go into any of the details. I just ran this one experiment. It took me a couple of hours one afternoon before it was a couple of days before the proposal was due, and I got that figure in there. So showing a little bit of evidence that your idea is feasible, I think really will strengthen that proposal. You don't want to obviously do too much preliminary work, otherwise you might not convince the reviewers that the work is necessary. There's work led to lots of things, lots of future directions. We're looking at controlling the temperature of the evaporation zone now, to see if we can control our evaporation during capillary flow better that way. And just to summarize here are kind of the key points that I went through. We want a project that has very high impact. We want to address a compelling problem. We want to be able to do that by studying a fundamental process, evaporation during capillary flow, using very simple experiments, ones that are amenable to our population, our undergraduates. I work exclusively with undergraduates, and I think cultivating that team is again, a critical component of success. I work with anywhere from 6 to 10 undergraduates at any given time, and structure the project so that they can contribute even within their own time constraints. So with that, I'd just like to thank all the students that worked on this project, a couple of collaborators, and also take the opportunity to thank Frank, who's been both a friend and a mentor over these past 11 years. So thank you, Frank, for all your support.
Thank you, Andres. Great talk. So I have a question for you.
Perfect.
What do you think was different about this RUI compared to your previous proposals that were unfunded?
I think and this may be specific to my field, but I was trained in a lab that did engineering. And so my first few proposals, I think, were more focused on just talking about all these cool things I could do. Hey, look, I can make this cool device. And it wasn't until I kind of took a step back and said, hey, instead I'm going to study this phenomenon. I'm going to study evaporation during capillary flow. I'm going to do some good basic science. That was the proposal that got funded. So at least in my mind, I think that was the key difference, was that the proposal have this component of contributing some fundamental new knowledge to our to the community.
Great, thank you, Andres.
Thank you, Frank.
So I'd like to thank everybody for presenting today. You all did a fabulous job. Speaker contact information will be shown in a little bit. For more information on any of the presentations, please contact the speakers directly, as this could lead to a collaboration or proposal opportunity. In addition, a link to the webcast will soon be made available on the STEMnet website. For more information on this webcast, please contact Michalak or myself, and previous webcasts can be found on our website. STEMnet's always looking to collaborate with faculty across the CSU campuses, and in fact have submitted, I believe, 8 proposals over the past 8 months with 11 institutions, and in fact have just submitted one yesterday with Long Beach, San Francisco, San Marcos, LA, and San Bernardino. So by all means, if you have an idea, please send me an email. And finally, prior to my arriving at the Chancellor's Office in 2019 as Executive Director of STEMnet, I had a fulfilling career in the Department of Chemistry at Cal State LA. From day one, I neither considered my faculty position a job nor work. It was a career and one I embraced with passion, for I was doing something I truly enjoyed. And I think some people alluded to that in terms of their careers here today. Perhaps much of this stemmed from my parents, both retired teachers. Furthermore, the fulfillment derived from teaching and working with students, discovering things no one else had ever seen or studied before, and seeing students matured over time made it all the more worthwhile. Of the nearly 150 undergrads, masters, high school students, and postdocs that worked in my labs for over 25 years, there are some I remember with certain fondness due to the impact research has had on their lives and how both they and I were affected, in other words, far and beyond the research paradigm. Very briefly, here is one of their stories. In 2011, one of my then current research students showed up in my office, and with his friend Hector, a recent transfer from a community college. He was a bit rotund, and I say this with affection, as over the years he would make a reference to his weight in many of our conversations. Hector Camacho was a recent transfer, majoring in biochemistry, interested in doing research, and he made it known he had not taken college too seriously up to then, as his grades would show. At that point, he was 27 years old, but he had recently had an epiphany and realized it was time to grow up, and was committed to changing his lifestyle, which foremost meant taking school seriously and getting involved in research, which he felt would further help ground him. He wanted to become a dentist, and felt this experience would help him achieve that goal. He started slowly, working with a senior undergrad in my labs. Over time, I came to realize there was something special about Hector, as he showed a drive, passion, and interest in his research few others in my group bestowed. He soon took on greater responsibilities. What was special about Hector was that he embraced challenges. I found he lived with a single mother and helped to support her. He drove limousines at night and found ways to live as cost-effective as possible. He was a go-getter, a hustler, and a survivor. He became a mentor to others in lab, and I could rely on him to get things done. A few years ago, I cracked one of my wisdom teeth on some food and needed a consult. The first person I turned to advice was Hector. Then, Dr. Hector Camacho. He responded from New Orleans, where he was completing his endodontics residency, and said, "Don't get it fixed. Take it out. You don't need it." After graduating from Cal State LA, Hector was one of the few to enter UC San Francisco's dental school. He once told me his undergraduate research experience made all the difference to him. It helped him secure his dream. A quick story before I end. Like myself, Hector is an avid Dodgers fan. In 2007, the Dodgers were in the World Series, and I texted him when they made it. We had both waited decades for the Dodgers to reach the World Series. Hector said he was boarding a plane from New Orleans to LA to catch Game 1. He said he's put all his patience on hold. There was no way in the world he was going to miss this game, and I laughed. Hector achieved his dream, and last year so too did many of us Dodger fans. So to all of you, be safe, and may the rest of your day be a happy one. I now turn it over to our own Jennifer Wicks for a few closing remarks.
Thank you very much, Frank, and thank you for sharing that personal story. Really inspiring. I want to, as you said, wrap with some information for everyone as we close today. We have the Webcast feedback survey on the left side. You'll see the link there, as well as the CSU STEMnet community listserv link. So please do join that if you haven't already, and begin a conversation with colleagues and join our private CSU STEMnet Facebook group. The link is there for you as well. Coming up, we have the Virtual Research Cafe 10.0 on June 30th. Please do register using that link to the left of your screen. And the STEMnet July webcast will be on July 22nd. You'll be hearing more about that coming up in the very near future. Excellent. So with that, I'd like to again thank you, Dr. Gomez, and all of these excellent presenters and researchers today for sharing their depth of knowledge and projects that they're currently working on. We really appreciate your time this morning. And I also want to thank Monica Alarcón from the STEMnet team, who has put together this session along with Dr. Gomez behind the scenes. She has joined us today. And I want to thank our student production assistant, Kayla Perez, as well, for her excellent help. And with that, we'll send you off to the rest of your day. Thank you, everyone, for your time. And the recording, again, will be up on the link that Monica has pasted in the chat pod. So have a great rest of the day. We'll see you again very soon. Bye for now.